Section 3.2, Vectors, Calculus of Vector Value Functions. Your homework for this section are numbers 41, 45, 49, 51, 53, 63, and 69. To study the calculus of vectored valued functions, we follow a similar path to the one we took in studying real valued functions. First, we define the derivative, then we examine applications of the derivative, then we move on to finding integrals. However, we will find some interesting new ideas along the way as a result of vector nature of these functions and the properties of space curves. We'll begin with the definition of the derivative. The derivative of a vectored value function r of t is r prime of t is equal to change of t as it's approaching 0 of r of t plus change of t plus r of t divided by change of t. And just as before, if you're working on a closed interval, in order for that derivative to exist, the limit from the left and the right must be the same. Let's do that first example. Use a definition to calculate the derivative of the function. So we have our derivative definition right above, just like your derivative definition of calculus. So as before, you can always use derivative definition, or you can always use your other rules you've learned, such as your power rule. Theorem 3.2. Let f, g, and h be differentiable functions of t. 1. If r of t equals f of ti plus g of tj, then r of t is equal to f prime of t I plus g prime of t j. Similarly, for three components, if r of t equals f of ti plus g of tj plus h of tk, then the derivative r prime of t is equal to f prime of ti plus g prime of tj plus h prime of tk. So to find the derivative of these next problems in this example, for that first one, we want to find the derivative of r of t is equal to 6t plus 8i plus 2t squared plus 2t minus 3j. So let's go ahead and take the derivative, and just as our definition, our theorem says above, we apply it to each component separately and kind of treat it like its own function. So that we have 6 for 6t plus 8i plus 8t plus 2j. And that's our derivative for r prime of t. Next one, we have r of t is equal to 3 cosine ti plus 4 sine tj. So just to recall, the derivative of sine of x is cosine, and the derivative of cosine x is negative sine. So recall these basic ones, because those are the ones you see all the time. All right, so for our first one, let's go ahead and apply these derivatives. We have 3, derivative of cosine is sine, negative sine. So I have negative 3 sine of t. And then we have the derivative of sine is cosine, so we just have 4 cosine of t j. And that's it. Not so bad, right? But as we move forward, all these other rules of differentiation that we've learned in the past don't go away. So let's take a look at example C. We have r of t is equal to e raised to the t power sine ti plus t raised to the t power cosine tj minus minus e raised to 2t power k. So as we take a look at each component separately, we see that for our first two, they're being multiplied, right? Maybe I shouldn't use dots because we reserve that for dot products, but they're being multiplied. So I have to use that product rule we learned way back when. Oh, that you learned in your Calculus 1 class. We didn't learn it specifically here. So remember, your definition is you take the derivative of your first one times your second plus a derivative of your second times your first, right? So for this one, we'll get the derivative of e is e. So we have e to the t sine t plus derivative of sine is cosine. So we have e to the t cosine t. That's I. Then we have the same idea for our next component. So I have e of t cosine t, the derivative of e is e, plus, well, the derivative of cosine is negative sine, so I should input that negative, e of t sine t. It's supposed to be a plus, but I wrote that minus since the derivative of cosine is negative sine. And lastly, the derivative of e to the 2t is e to the 2t. We take the derivative of our numerator, of our exponent, which is 2. So there we get that. Okay. And all we can do to kind of clean up our answer is maybe factor out those e's for each one. So that we have e to the t sine of t plus cosine of t I plus e to the t cosine t minus sine t and minus 2 raised to the e to the 2tk. That is our answer. I hope you found these last 3 examples enjoyable. They're pretty fun. The next ones, they're not hard. There's just a lot going on. So be very careful with your steps. Theorem 3.3. Properties of derivative of a vector valued function. Let R and U be differentiable vector valued functions of t. Let f be a differentiable real valued function of t, and let c be scalar. First, we have the scalar multiple rule. The derivative of c r of t is equal to c r prime of t. 2. The derivative of r of t plus u of t is equal to r prime of t plus u of t. Exactly like our example above. Now, it doesn't matter if it's a sum or a difference. The same idea applies. R prime of t of u of t times f of t times u of t is r f prime of t u of t plus f of t u prime of t. That's called your scalar product. I always translate it in my head as the product rule that you learned in Calculus 1. Next, that's new to us, d of t of r of t dot product u of t, that is equal to the derivative of r of t dot product u of t plus r of t dot product u prime of t. Next, we have cross product. The derivative of r of t cross product u of t is equal to r of t cross product u of t plus r of t cross product u of t, u prime of t. 6. D of t is equal to r of f of t. That is equal to r prime of f of t dot product f prime of t. That's your chain rule. And lastly, the dot product of r of t and r of t will result in a scalar, a constant. And the dot product of a function and its derivative is equal to 0. So r of t dot product r prime of t will result in 0. And we're going to use this one in one of our examples. So this is where you saw it first. Okay, first example. Well, next example. Given the vector value functions, calculate the following derivatives. R of t is equal to 6t plus 8i plus 4t squared plus 2t minus 3j plus 5tk. U of t is equal to t squared minus 3i plus 2t plus 4j plus plus t cubed minus 3tk. For A, we want to find r of t dot product u of t. Okay, so here we have it, and I want to find the dot product of r of t and u of t. According to our definition right above, for that dot product, I need to use a derivative of both of them, right? So just to rewrite what this is, our definition for the dot product, we have r prime of t, of your first one, dot product your second, u of t, plus the first dot product derivative of your second, so u of t. Now, since we're going to be using the derivatives, let's just go ahead and take those derivatives from the beginning, and then let's go apply the dot product. So r prime of t, that's equal to 6i plus 8t plus 2 plus 5. U prime of t is equal to 2t plus 2j, I forgot the I, plus 3t squared minus 3. Okay. All right, now let's go ahead and use that definition right above. So we have, for the first one, r prime of t dot product u of t. So I'm just going to write it down. R of t is 6i plus 8t plus 2j plus 5k. And I'm going to dot product that with u of t. U of t is t squared minus 3i plus 2t plus 4j plus t cubed minus 3t. Okay. That's only the first part. Then I'm going to add the dot product of r of t dot product u of t. So r of t is, r of t, we have it right here, is 6t plus 8i, 4t squared plus 2t minus 3j plus 5t k. And we're going to dot product that with u prime. U prime is 2ti plus 2j plus 3t squared minus 3k. Okay, now recall dot product. We're going to multiply our i's of our vectors, our j's, and our k's, and then we add them. Let's start off by multiplying our i's. That's why I'm always so careful marking our I and j's, because I often would confuse them. All right, so for our i's, we have 6 times t squared minus 3. That gives us 6t squared minus 18. Okay, next we have our j's. So for our j's, we have to multiply them, so we have to FOIL. So 8 times 2, we get 16t squared plus 32t plus 4t plus 8. Okay, next we have our k's. So I have 5k times t cubed minus 3t. So that we have 5t cubed minus 15t. Plus, so we're going to add that up with our next dot product. All right, so that we have, first we have our i's, 6t dot product, 6t plus 8 dot product ut. That gives us 12t squared plus 16t. Our j's, let's multiply those so that we have 8t squared plus 4t minus 6. And then lastly, let's multiply our j's. 5t times 3t squared plus 3t. 15t squared minus 15t. Oh, that should be a cubed. 5t times 3t squared is 15t cubed, and then minus 15t. Okay, our answer will be adding up all of these like terms. We should get 20t cubed plus 42t squared plus 26t minus 16. Next one. All right, so this one is being very specific, so look at it carefully. It's asking for u of t cross product u prime of t. Now, by our definition above, I'm going to bounce back so we can see it. When taking the derivative of the cross product, we want our derivative of our first cross product our second plus a derivative of our first cross product derivative of our second. Kind of like product rule, but with cross products, right? Now let's go ahead and apply it to what we're given, which is u's. So that we have, this would give us u prime of t, cross product our second, which is u prime of t, cross plus our first, which is u of t, cross product the derivative of our second. So our second is u prime. The derivative of u prime would be u double prime. Okay, so this, we're taking that definition and applying it to what we have. Now here we have u. We're going to need u prime. So you can recall it from the past, or you can just take the derivative all over again. So that we have 2t I plus 2j plus 3t squared minus 3k. And u double prime will give us 2i plus 0j plus 6tk. Now, based on our rule or definition above, notice that if I have the cross product of two derivatives, that gives me 0. Right? We had that right above. The derivative of r and its derivative is 0, which is how it applies here. Okay, so now we're just left with to work out with this. All right, so we have to just find u of t cross product u prime of t. Okay, well, u of t, let's set up our matrix. We have I, j, and k. I is, well, we first have that u of t. U of t is t squared minus 3, 2t plus 4, and t cubed minus 3t. U double prime is t, oh no, not t, it's 2, 0, and 6t. Let's go ahead and find the cross product. So I always make mistakes with cross products, so I like to write it vertically. So the cross product of I would be, so we block those. We have 2t plus 4, t cubed minus 3t, and 0 and 16. For j, we have minus, and that will be t squared minus 3, and t cubed minus 3t, 2 and 16. And for k, we have t squared minus 3, 2t plus 4, 2 and 0. Let's go ahead and find the cross product, or the determinants of those 2 by 2's. So that we have, while we multiply across, we have 2t plus 4 times 16. That gives us 12t squared plus 24t minus, well, anything times 0 is 0. And then we have 2t minus 3 times 6t will give us 6t cubed minus 18t minus 2 times t cubed minus 3t. So that gives us 2t cubed minus 6t. And for our k, we have anything times 0, 0, minus 2t plus 8. Okay, let's clean these up. So here we just have 12t squared plus 24t. Here I have to distribute that negative. Let's combine like terms so that we have 6t cubed minus 2t cubed, 4t cubed. And then negative 18 plus 6, we have minus 12t. And here we distribute that negative, and we're left with negative 2t minus 8. Now for this first one, for the second one, don't forget to input that negative. So actually, this gives us negative 4t cubed plus 12t. So we have our I, our j, and our k. And our answer, our final answer would be 12t squared plus 24t plus, well, I want the minus in between, so I can just switch them, right? 12t minus 4t cubed j plus, or I can factor out a negative, your call, negative 2t minus 8k. Not so bad. Be very careful with your cross products of 3 components. There's a lot of room for silly mistakes. Tangent vectors and unit tangent vectors. Recall that the derivative of a point can be interpreted as the slope of a tangent line to the graph at a point. In the case of a vector value function, the derivative provided a tangent vector to the curve represented by the function. Let C be a curve defined by a vectored value function r, and assume that r prime exists when t equals t naught. The tangent vector v at t equal t naught is any vector such that the tail of the vector is placed at the point r of t naught on the graph. The vector v is tangent to the curve C. Vector r prime t naught is an example of vector point at t equal t naught. Furthermore, assume that r prime of t is not equal to 0. The principal unit tangent vector at t is defined as T of t is equal to r prime of t divided by the magnitude of r prime of t. Okay, let's do an example. I'll do the first one with you. I think you'll be able to do the second. Now, you know how to do this. We're just applying this new idea and this new definition. So to find the unit tangent vector for our first example, it reads, find the unit tangent vector for each of the following vectored value functions. All right, well, we need the derivative and then the magnitude of the derivative. Remember, the magnitude is just the square root of each value squared, right? So you can do that. You just need to start off with the derivative. So for a, I need to find r prime of t. R prime of t, well, derivative of cosine is sine, negative sine. So I have sine t, negative sine ti, plus derivative of cosine, derivative of sine is cosine, cosine of t, j. Okay, well, let's go ahead and take the magnitude. The magnitude of r prime of t is equal to negative sine of t squared plus cosine of t squared, square root. Now, what's helpful here is your Pythagorean identity. Recall that sine squared t plus cosine squared t is equal to 1. Okay, so then to find our unit tangent vector, t of t is equal to r prime of t divided by the magnitude of r prime of t. All right, well, the derivative is negative sine of t I plus cosine of t j divided by, well, we saw that our square root is just square root of 1, which is just 1. So that our answer is negative sine of t plus cosine of t divided by 1. So we just get that back in return. So we get negative sine of ti, I forgot the I above, plus cosine of t j. Not so bad, right? Just taking one step at a time. Here I wrote this backwards. It's always in arguments of t, since we have f of t, and I, j, and k are telling you the component. I think you can do this one. Just remember, you need to find u prime of t, and then the magnitude of that. And you can go ahead and check your work in your book if you're unsure about it. Integrals of vector value functions. Just as we calculate the derivative of a vector value function by differentiating the component function separately, we can calculate the antiderivative in the same manner. Also, the fundamental theorem of calculus applies to vectored value functions as well. Definition of indefinite integral and definite integral of vectored valued functions. Let f, g, and h be integratable real valued functions over the closed interval a, b. The indefinite integral of a vectored value function r of t equals f of ti plus g of tj is the integral of f of ti plus g of tj dt is equal to the integral of f of t dti plus the integral of g of t dtj. The indefinite integral of a vector value function is the integral from beta a of f of ti plus g of tj dt is equal to the integral of from beta a of f of t dti plus the integral from b to a of g of t dtj. All of this also applies to three components. Calculate each of the following integrals. So I'll set up the first one, and I'm very confident you can do the first one. So according to our definition above, our integral for our function, our vectored value function, extends and can be applied to each component of our vectored valued function. So that we have A. Calculate each of the following integrals. For A, we have the integral of 3t squared plus 2ti plus 3t minus 6tj plus 6t cubed plus 5t squared minus 4k dt. All right, so I can apply the integral, the antiderivative, to each of the following components. So that I have the integral of 3t squared plus 2t dti plus the integral of 3t minus 6 dtj plus the integral of 6t cubed plus 5t squared minus 4 dt k. Okay, we can do this one really quickly. So you just take the integral of each term within each component so that you have t cubed plus t squared I plus 3 over 2 t squared minus 6t j plus 3 over 2 t to the fourth power plus 5 over 3t cubed minus 4t k, and as always at the end plus c, unless we have a closed integral. Okay, let's do b. B is different for us. So I want to calculate the integral for these vectors and the cross product. So we first need to calculate the cross product. So we have our ijk of t squared, and t cubed. And second, I have t cubed, t squared, and t. Let's go ahead and find the determinant. Well, the cross product, not determinant. We don't call it determinant. So then we have I minus j plus k. All right. So for I, we have t squared and t cubed and t squared and t. For j, we have t and t cubed and t. And for k, we have t and t squared and t cubed and t squared. Okay, let's go ahead and multiply across. So we have t cubed minus t to the fifth power I minus t times t is t squared minus t cubed times t cubed is t to the sixth power j. And then we have plus t times t squared is t cubed minus t to the fifth power k. All right. One more thing we would do, for the sake of not having the negative on the outside, I'll multiply it in. So that we have t cubed minus t to the fifth power I plus t to the 6 minus t squared j plus t cubed minus t to the 5th power. Okay. All right, we go ahead and now that we first took the cross product, I can go ahead and now apply the integral of that, or antiderivative. So we can take the antiderivative of each component separately so that we have the integral of t cubed minus t to the 5th power for I plus the integral of t to the 6th power minus t squared k plus t cubed minus t to the 5th power k. And we should be writing dt for each one of them, right? And for our answer, we get t to the 4th power over 4 minus t to the 6th power over 6 I plus t to the 7th power over 7 minus t cubed over 3 k plus t to the 4th power over 4 minus t to the 6th power minus 6k plus c. All right, and lastly, we have one more example to do. Now it's bounded, right? It's telling us the closed interval for which you want to apply this antiderivative. So our problem is the integral from pi over 3 over 4 of sine 2ti plus tan tj plus e raised to the negative 2t power k dt. Okay, so just as integrals work, we apply it to each term. In this case, we say component, right? So we take the the integral of each component of our vectored valued function so that we have from pi over 3 to 0 of sine 2t dt I plus the integral of pi over 3 to 0 of tangent t dt j plus the integral of pi over 3 to 0 of e to the negative 2t dt. Okay. All right. So for this problem, I would have my unit circle handy just so I know what those values are as I'm integrating, right? So let's first start with integration. The derivative of sine is cosine. Well, the antiderivative of sine is negative cosine. So we have negative cosine of 2t, and because we have to consider our argument 2t, we get that 1/2 from pi over 3 to 0. And then we have the antiderivative of tangent is ln cosine. So we have ln cosine, negative ln cosine of t from pi over 3 to 0. And then the derivative of e to the 2t is negative e to the 2, well, e to the negative 2t, and we take derivative of our exponent, which gives us negative 2 from pi over 3 to 0. Okay, now we just need to go ahead and plug in our boundaries so that we have negative 1/2 cosine at pi over 3 minus negative 1/2, so I'll write a plus 1/2 cosine of 2. I forgot that 2 in that first one. It's 2t, right? So 2 times 0. Next one we have minus write a little parentheses so I don't lose track of that minus the ln of cosine at pi over 3 minus the ln of cosine at 0. And then we have minus, I'll factor out that negative so that I have 2 e to the negative 2 times pi over 3. And then we'll have minus 2 e to the negative 2 times 0. Okay, let's clean this up. So this gives us 2 pi over 3. Cosine at 2 pi over 3 is negative 1/2. So then we have negative 1/2 times negative 1/2, we get 1/4. Cosine at 0 is 1. 1 times 1/2 is just 1/2. And then here your book has a typo. So if you're following my notes and following the book, there is a typo there. Cosine at 0 to begin. Cosine at 0 is 1, so we have ln of 1. Ln of 1 is just 0. And here we have cosine at pi over 3. Cosine at pi over 3 is 1/2. So we're left with ln of 1/2. So minus ln of 1/2. Your book has ln of 2. That's a typo. Okay, well, moving forward, we have, well, here it just becomes negative 2 pi over 3. And we can't really do anything with that. And then here we have raised to the 0 power. Anything raised to the 0 power is just 1. Now let's multiply that negative. So then this turns into, the first term is a minus, second term is positive. So that I have plus e to the negative 2 pi over 3. Ooh, that should have been over 2, not times 2, over 2. Over 2 minus 1/2. And then that is our answer. All right, that's it for our section. Section 3.2, vector calculus of vector valued function. And there is your homework. Thanks.